Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about motion in space, so specifically in 3D space, and we're going to talk about how velocity and acceleration applies to that 3D space. So, okay, let's just get right into it. So in this section, we show how the ideas of tangent and normal vectors and curvature can be used in physics to study the motion of an object, including its velocity and acceleration along a space curve. So in particular, we follow in the footsteps of Newton by using these methods to derive Kepler's first law of planetary motion. Okay, so let's just hop right into it. So we're going to introduce ourselves or review. It's more like a review from Calculus 1. This idea of velocity, speed, and acceleration, right? So what again are these three things mathematically? Well, intuitively, right? Speed is how fast you go. Velocity is the direction, right? Velocity includes direction. So velocity is speed with direction. Speed doesn't have direction, right? So that's why the absolute value of velocity, or I think it was the other way around. No, it's this way. It's just speed. And then we have acceleration, which is, well, if we take the derivative of these things, we get acceleration because it's that change in velocity and change in speed. Are we accelerating? Are we decelerating? So that's the intuitive version. Now let's dive into a mathematical version here. So of course, it's going to start with a particle. Um, Obviously. And this particle is moving through a 3D space. So it's moving through our 3D space, right? So we have a position vector. Okay. And we'll say our parameter is t, and we'll say t is time. And we're going to denote our position vector as a vector function. So this will give us the corresponding position after t equals, or after some time t. Okay. And then here is I'm going to show a visual here real quick. So that's the initial background there, or what do you call that? Scenario. The initial scenario. So here's our guided figure. So here we notice, okay, this is our space curve. So that's the trajectory or the path at which the particle is moving. So it's either the particle's moving that way or the other way. But it seems like it's moving the previous way I just said. And then here we have a vector r of t. So this will tell us exactly where we are after some time t, right? And then here we have its tangent vector, so its derivative, right? And then we also have the limit definition of its derivative here. And we're able to get this after we have our vector r of t plus some value h that we don't know. Right? So that's the intuitive definition. No, not even intuitive. That's a mathematical way of looking at, uh, if I'm not mistaken, the direction of the particle. So yeah, that's actually our first definition here. We're going to be looking at um, r of t plus h minus r of t over h. So that's that blue vector here, right? And this will tell us the approximate, or this will approximate the direction of the particle moving along the curve r of t. Its magnitude, so if we get the magnitude, it actually measures the size of the displacement vector per unit time, right? So the vector from 1 gives the average velocity over a time interval of length h, right? And its limit is the velocity vector v of t. Let's just name it v of t at time t. So let me just say a few words about this. So another definition that we want to look at is its velocity vector is the limit as h approaches 0 of this thing here. And this is just basically its derivative, right? Okay, okay. I hope that makes sense. Yeah. So basically, the first one is telling us, well, the approximate direction of the particle. So if we were to have these 2 points, then we have a vector that can kind of connect them, which is this blue vector here. And that's to approximate the direction of that curve. So this is actually a secant vector. And then this r prime of t tells us, well, it's the derivative at that point, r of t. And then this r of t plus h is another point on that trajectory or that path. And then this is an estimate. And as that t approaches 0, or if it reaches 0, right? Let's say this is my h. Oh God, that was a bad drawing. This is my h, right? As it's 0, well, it's basically just going to be r of t. And so as we get the limit of that h, so a calculus 1 concept, as we get the limit of that h as it approaches 0, so this thing is going to go here. Then we're going to get r prime of t, right? Because if we're here, we now have r of t, and we get this tangent vector. And so that's the idea. So thus the velocity vector is also the tangent vector. Velocity vector is the tangent vector. And points in the direction of the tangent line. We have a tangent line, it's in red. And there's a point or a direction. So it's a tangent line with a direction. And the speed of the particle at this time t is the magnitude of the velocity vector. So what I said previously, if we get the magnitude of our velocity, we will get our speed. So I mentioned this earlier, which is part of an intuitive definition. What else? Okay, this is appropriate because from our second definition here, so our V of t definition, well, we can say that, oh, the absolute value of this, our velocity, is our absolute value of my tangent vector, right? I'm just getting the absolute value of this, right? And so what does that mean? Well, this is actually just from a previous lecture on, I think this was arc length and curvature. This is actually just, I'm going to explain what this dsdt means. It's the rate of distance, of change of distance. Change of distance just means speed with respect to time. So another way to write this, which is my preferred way, that was the textbook way, it's in Leibniz notation, is S prime of t. That's my preferred way of writing it. But I'm just going to follow the textbook. There's usually, if they write it in a certain notation, it's helpful to write it that way than the other way. But yeah, we're going to see. If not, then that's all right. So as in the case of one-dimensional motion, the acceleration of the particle, so if we look at 1D or in one-dimensional motion, well, the acceleration of the particle is defined as the derivative of velocity. So the acceleration is the derivative of the velocity. So here I'm writing it in my notation. And believe it or not, it's the double derivative of my position. So this is my position. I think it's double derivative. I get a of t. I get the derivative of my position. I get my velocity. Okay, let's do an example because I don't want to get bogged down by theory. So example one. So we say that the position vector of an object. Oh, what was that? Of an object is moving. Oh wait, the position vector of an object, and let's say it's moving in a plane. So it's in a plane. So when I say it's in a plane, it's 2D. So I'm just gonna say that moving in a plane. Doesn't matter what plane it is. It could be the XY plane, could be the, I don't know, a plane with XYZ is R of t. So that's our position vector. T cubed I plus t squared j. Now, you know I'm not a big fan of this ij notation, so I'm going to write it in vector form. So we know this is in 2D. And here we're being asked to find its velocity, its speed, and its acceleration. Specifically, when my parameter t is 1. Okay. So first, let's find velocity. Let's do that. So when we find our velocity, this is our position, right? So we want to just take the derivative. So we get v of t. Oh, my bad. It's just the derivative of my position vector. So instead of t cubed and t squared, I take its derivative. So 3t squared, 2t. So again, calculus 1 course on derivatives. So please check that out. And now let's do it as well for, actually that's easy. Let's do it as well for acceleration. Speed is just we're getting the absolute value of v of t and r prime of t. So for acceleration, well, it's just the derivative of my velocity vector which is the double derivative of my position vector. And so that's just, well, 60 and 2, right? And sure, let's calculate speed. Why not? Let's just do it all in one line here. So my speed is, well, I don't know how to denote speed. I'm just going to say absolute value of my velocity. And so I get the distance of this thing. 3t squared squared. Should I have done that? I don't think I should have done that. Because it would have been easier to just plug it in. Who cares? So let's just do it. Actually, no, let's not do it. I'm not going to do it that way. The textbook did it that way. I'm not going to do it that way. Here we find v of 1, right? Velocity, speed, and acceleration when t is 1. So my v of 1 is 3 and 2. My a of 1, or my acceleration, is 6, 2. Okay? So those are those are two things. Oh, I almost forgot. And my absolute value at 1. So my speed as well. See how easy it is? You just square it. Then I get 9 plus 4. Don't ask why I'm doing a calculator. I get square root of 13. Yeah, I'm that guy. Okay. So now we've got the velocity, acceleration, and speed at t equals 1. And what else? What else? What else? Now we can draw. We can see how this looks like. So if we draw this, well, I'm going to draw it myself actually. Just bear with me. If we actually draw this, okay, so I think it wants us to assume, because I'm looking at my task book, it wants us to assume that we're doing it in the xy plane. So cool, let's do it that way then. And we have a curve. So curve is our position vector, right? And our curve is t cubed t squared. And so if I actually just get that, that's the slope, I believe. Will I get something like 1 over t? I'm sure that's super accurate. What's that gonna look like? Let me double check, because I genuinely don't know. I'm not a big fan of graphs anyway. Okay, so my graph is showing me something different. Okay. Let me see. Yeah, my speed is that. My position. How in the world did he graph that thing? Or he did a different one. T equals 1. Oh. Oh, okay. So if we were to graph this, apparently its trajectory would look something like this, right? Now, we have the point. Why is this 3, 2? What? 3i plus 2j? A1? Okay. Oh, then we use our position vector. But at t equals 1, that's just 1, 1. Right? If we do our position vector at 1, it's just going to give us 1. 1 and 1. So this is just 1, 1. Okay. And then what else? Now we can draw our velocity and our acceleration vectors. So our velocity goes 3 to the right and 2 up. So it maybe I'll I'll do a 4 here. 3 to the right, and then 2 up. So maybe I'll do a 3 here. So here, here. So maybe it's pointing something like that. My V of 1. Specifically my V of 1. And then for my acceleration, well, it's a 6 to the right and 2 up, right? Because here's just the change in x. So I go positive x 6 times and positive y 2 times. So I do 6 to the right, 2 up. So maybe, was this 1 plus 6? So maybe like 7 here. That's not drawn to scale. And then 2 up, so same, it's just 3. So 7, then up maybe here. So it would look something like that, right? Okay. Interesting. Another way we could have done the trajectory, this thing, this is our trajectory, right? Another way we could have done that was to just plug in points in our position vector and then get something out of it, right? Or we could just graph it in code or something. Okay, so that's example 1. Now in example 2, we're going to go 3D. So let's do 3D here. We're again being asked to find the velocity, the acceleration, what else? And speed. Oops, and speed. Of a particle. So we're doing it again with the particles. With, okay, we're gonna say a position vector. And this position vector, we're gonna name it r of t. So it's a vector function. And it's in vector form, thank goodness. So t squared e of t, te, oops, what was that? te to the power of t. Okay. Now, well, let's solve it, right? So we find our velocity, acceleration, and speed. I'm not even gonna. So to find velocity, we just, again, we take its derivative. So the derivative of t squared is 2t. E to the t is just e to the t. T times e to the t. Let me do that real quick. I think I've done it many times in previous videos. But I'm just gonna do it real quick. E to the t. So here I did a product rule. And this is e to the t plus t. Then this is e to the t. Oh, and I get e to the t 1 plus t. Okay. Yeah, so if you want to review on derivatives, fine. I'm gonna make some videos on calculus 1 and 2. But I'm gonna do it in a fun way. I don't want to do it like this textbook. Yeah. Okay. And then we get our acceleration vector. So I'm not gonna write the whole like sequence anymore, but basically we just take the derivative of our velocity vector. So this gives us 2 e to the t. And then we do another product rule here. E to the t of this times this. We add e to the t of this times the derivative of this. So this is just e to the t. There's 1 plus t. Here, this is 1. And so I have e to the t 1 plus t plus e to the t. Okay. Now I think I can simplify, right? e to the t plus t e to the t plus e to the t. Now I can factor out my e to the t altogether. I get 1 plus t plus 1. Oh, look at that. Voila. I get 2 plus t, or t plus 2. Okay, that's fun. Okay. Um, Let me see if I got that correct. Okay, got it. Okay. And then I get my I get my absolute value here, because now I want to find its speed. So I'm just gonna get the absolute value of my velocity. Wait, is there a specific? Oh, there's none. So I do it in terms of t. Okay. So I get 2t squared plus e to the t squared plus e to the t 1 plus t squared. Now maybe I can sort of expand here. So here I get 4t squared plus e to the 2t, right? I could do that. Plus, I'm going to expand here. I get e to the t plus d e to the t squared. And then from here, maybe I might just plug it in. Or no, I actually can't do that. Yeah, I have to do it twice. D e to the t. And I do it again. So this is annoying algebra 101. And then we multiply. So we got e to the t. Square that. So we just get e to the 2t here. Plus this times this. So this is t e to the 2t, if I'm not mistaken. And I do it again. And then now I plug this in. So I get t squared e to the 2t. And here I just get 2t. How many times am I saying that? 2t e to the 2t. Now I can factor out a lot of stuff here. Now I can say, oh, I can factor out my e to the 2t, right? So I get e to the 2t. I get 1 plus 2t plus t squared. Oh, look at that. This is the same thing as, well, t plus 1 squared. And there we go. Yeah, I got it. Okay. I'm going to erase this. Derivatives. So now I get 4t squared plus e to the 2t plus e to the 2t t plus 1 squared. There's something about derivatives that make it annoying, and that's computing it. Okay. Next. So now we've got those. Actually, let me just. I'm just boxing my final answers here. Yeah, I like to box my final answers just so that if I need to use them, the formulas, I can just look at my boxed answers and see. Okay, I guess I don't need to. So now I mean, I don't want to, I hate drawing in 3D, from my experience. Um, okay. But here basically, now we can find them in terms of t equals 1, right? And here's how a graph of it would look like. A graph of it would look something like this. I'm just taking a screenshot. I don't like drawing these things. Okay. So this is how the graph looks like. And I'm gonna assume again that this is at 1, 1. Let me check. What's my R of t? I get 1, 1. No, I get 1 for my x. e to the 1 for my y, and again e to the 1 for my z. So yeah, that's something I can't do. Yeah, so this is now in 3D, basically. And then this is the trajectory. So again, I just keep plotting points to get that trajectory, the black curve, and that should be good. Okay, now just a couple of notes. But earlier in the chapter, we saw that a curve can be parameterized in different ways. But the geometric properties of a curve, so its arc length, curvature, are independent of the choice of parameterization. On the other hand, though, velocity, speed, and acceleration do depend on the parameterizations used. So based on how you parameterize your your curve, it will affect the velocity, the speed, and acceleration. So you can think of the curve as a road and a parameterization as describing how you travel along that road. And so the length and curvature of the road do not depend on how you travel on it, but your velocity and acceleration do. Okay, so the vector integrals that were introduced in, I think it was like 2 videos ago in my calculus series, can be used to find position vectors, right? Because if we take the integral of my vector, right? My what do you call this? My v, my vector, and let's say this is my velocity. Well, I'm just gonna get my position back, my r, which I'll say is my position. Um, yeah, so it can be used to find position vectors when velocity or acceleration vectors are given or are known. Okay, let's look at that example. Actually, let me write notes on the previous one. So what I'm saying is so I'm just gonna write like note. Ooh, green looks nice. I'm saying that velocity, just on the previous thing I yapped about, velocity, speed, and acceleration depend on parameterization. So depending on how you parameterize, it will affect your speed, velocity, and acceleration. Because imagine this, if you're going to some place, let's say you're going to UW, because I'm from UW, you're going to UW, and there are multiple ways to get to, let's say, Suzzallo Library. There are multiple ways to get to Suzzallo Library, starting from, I don't know, you're eating at Cafe on the Ave. And so if you parameterize, if you make parameters of X, Y, Z, right? Or X, Y, doesn't matter. Well, there are ways where you can get to Suzzallo faster, right? Because you're making a path, you're making a curve. There are certain paths or curves that go to Suzzallo much quicker compared to other paths. So that's the idea. Your velocity. So yeah, if you walk towards Suzzallo from Cafe on the Ave, well, it will depend on how you parameterize your curve or how you made your path going from Cafe all the way to Suzzallo. That's a practical example. And I think pretty sure Google GPS also does that. They have like, I don't know, an optimized, they're probably optimizing, they have an optimization algorithm somewhere that tells them, oh, what's the quickest path or curve going to this place? Or what's the quickest way to go here despite traffic? So stuff like that. So pretty interesting stuff. But yeah, okay. Before I yap, let's go to another example. Before I yap about other stuff. So here again, we have a moving particle, obviously, again with these particles. And this moving particle starts at position r of 0. So at time 0, it starts at r of 0, and it has these components, xyz components. And it has an initial velocity of, let's say, okay, not of, initial velocity. So at time 0, so v of 0 is I minus j plus k. Let's actually translate that immediately because I don't like saying that. So I is 1, 0, 0. Okay, let me do it in another. So to translate this, because I just want to do it, I don't like ijk. 1, 0, 0, that's my I. So these are standard basis vectors, right? 0, 1, 0, that's my j. And I add it to my k. 0, 0. And this will give me, okay, 1 minus 0, that's 1. 0 minus 1, that's negative 1. 0 minus 0, that's 0. And I add it to this thing. And I continue. 1 plus 0, that's 1. Negative 1 plus 0 is negative 1. 0 plus 1 is 1. There we go. That's the vector. Simplified. So that's my initial velocity. We have an acceleration included. So it's acceleration. So we're giving it in terms of t, right? Is 4ti plus 6tj plus k. So let's just immediately translate it. 40, 61. And we're being asked to find velocity and position when at time t. So we're being asked to find v of t and r of t because we're not given those. Well, we did learn something about this, and it's called integrating. Right? So this was from, I think it was like what, 2 videos ago in my calculus series. So yeah, let's just find velocity first. So here we're gonna find v of t. And so the way to do that is to integrate my acceleration, and that will give me v of t. So my v of t here is integrating my acceleration. And so that means if I integrate a vector, well, I have to integrate its components. That's the thing in math. If you do something to one of them, you do something to all of them, or something like that. Okay. Now, what can we say? Let's do it one by one. So we have the integral of 40. Well, this is just 4t squared over 2 plus some constant, let's say c1. Well, this is 2t squared plus c1. So that's a constant, right? Let's do another one. 6t dt. Well, here we get 6 t squared over 2 plus c2. And we have 3t squared plus c2. The way to check if this actually works is to derive it again. So if we get the derivative, well, we get 40. And then this is constant, so it's just 40 plus 0, so 40. Okay, and then another one was 1 dt, which is just t plus c3. Good, now we derived it. Now I have to find my constants, right? So to find my constants, well, I have to have an information about V. So I have V of 0 here, which is equal to this thing. So I find my constants, C1, C2, C3, using what I know about V. And I know V is equal, when V is, or when time is 0, my velocity is the vector with components 1, oops, 1, negative 1, 1, right? Okay. And so I'm going to use that. So we have our function here, 2t squared plus c1. And we're going to say if t is 0, so 2, 0 squared plus c1 is equal to 1. And this will tell me, okay, my c1 is 1. Because this just becomes 0. Let's look at another one. 3t squared plus c2. So 3, 0 squared plus c2 is equal to negative 1. So here we say that c2 is equal to negative 1. Let's look at the last one. We have t plus c3 is again equal to 1. And here we say that t is 0. Well, this is probably the easiest. C3 is 1. And from there, we have our velocity vector, right? So my v of t has components, well, 2t squared plus c1. My c1 is 1. And then my y component is 3t squared plus c2. Plus c2 is minus 1, so I just do minus 1. And my c3, or my last component, z component, t plus c3. So t plus 1, because my c3 is 1. And there we have it. Oh, crap. That's my velocity vector. Now let's find my position vector r of t. So it's the same process. So now we find r of t. And we're saying that r of t is just integrating, again, my v of t. My velocity vector. So I want to integrate that thing. And integrating that thing means we also have to integrate its components. Okay, let's do it one by one. So we got 2t squared plus 1 dt. Well, this will give us, I think it was 2. What was it? This is 2 t cubed over 3 plus t. And then I add a constant. And then for my next one, 3t squared minus 1 dt. So when I integrate, I have 3 t cubed over 3 minus t. And I have c2. And I can actually, okay, let me just clean this up. I want it to look clean. 2 over 3 t cubed plus t plus c1. Okay, that looks nicer. And then here we have t cubed, right? Because I cancel out the 3's here. Minus t, right? Plus c2. And lastly, my final integral, indefinite integral, t plus 1. This will give me, okay, t squared over 2 plus t. And then some constant. Do I do 1/2? I'll just stick to this. And then again, I find my constants, right? Using the information I have about my position vector. So again, I find my constants C1, C2, C3. What do I know about my position vector? My r of something. Do I have that? Yes, I do. I have r of 0, which is equal to 1, 0, 0. That's my vector. Okay, now what? Well, now I can just plug in what I know, right? So at t equals 0, my x component is 2 over 3, 0 squared, plus 0, plus c1, I believe, is now 1. So this tells me c1 is equal to, I wrote 0, c1 is equal to 1. Okay, my next one is t cubed minus t plus c2. This is equal to 0. And here I just changed these to 0. Well, look at that. I get c2 is 0. And lastly, my t squared, so 0 squared over 2 plus 0 plus t, right? Plus c3 is again also equal to 0. So I have c3 is equal to 0. And then from there, I have my r of t. So my r of t is just, well, 2 over 3 t cubed. Then I add t, and I add 1. And then these are just 0, so I just write them as such. T cubed minus t. Then my other one was t squared over 2 plus t. So there's something about integrating that makes it really long. But yeah, that's my r of t. And if I didn't mess up, I should be correct. Okay, I got it. And yeah, we can use that r of t to make a path or a trajectory, right? Okay, so in general, vector integrals allow us to recover velocity when we know its acceleration, and position when we know its velocity. So actually, if we just know acceleration, we can get position and vector. Position, so the distance, and our vector, so our velocity, right? um. Okay, so I'm just gonna write that important fact down. So in general, if we know acceleration, we know velocity and speed. And this is not only for vectors. This is also for real valued functions, like our f of x stuff, right? So it would look something like this. We would know our v of t, which is just v of t naught, so our initial time. And then we add 0 to t of au du. Right? So we just take the integral of our a value. So this is the most general as it can get, right? Because we need our velocity at a given time. And if we just integrate this, so we get, yeah, we integrate this, we get g of t minus v of 0. And then our other general formula here is r of t. Okay, maybe I should write it in the other spot. My r of t is basically its initial time, and I add my I integrate my velocity vector. Here I'm just using a different parameter. Okay, so if the force acts on a particle, if the force that acts on a particle is known, then the acceleration can be found from Newton's second law of motion. So here we go to physics. So if we know our force, then we can find acceleration. So this is a physics concept. Okay. The vector version of this law. So here we're now applying something from physics, because from physics, or from high school physics, we can get our force, which is equal to mass times acceleration, right? That's a physics definition. Now, if we want to apply this in vector form, well, we can say that f of t is what? F of t is force acts on object. So some force that acts on the object with a mass. So we're going to say the mass is constant, a mass m, producing acceleration. Okay, let me write it here. And this acceleration also varies as time goes by and based on its force. And so from here, we basically have this formula. F of t is m of a of t, right? Okay, now I'm gonna move to an example, and then after this, we're gonna take a short break, maybe. Or I'm gonna take a short break. Because I know I don't want the video to be too long. Okay, so we're given an example here. We're saying that an object has a mass that moves in a circular path. So there's something about circular motion. So this object moves at a circular path. So again, it has something to do with parametric circular equations, right? And it has a constant angular speed. So this is something from pre-calculus, and we'll call it omega. And it has a position vector. It has a position vector, we'll call it r of t. And it's basically equal to a, which I assume is some radius. And then it has theta, not theta, omega t. So that's our angular speed, I plus a sine omega t j. And we're being asked to find the force acting on object. So find force of object, or that's acting on the object, and show it's directed towards the origin. So we're going to prove that in this case. So, okay. Well, to find the force, right, we need an acceleration. We have a mass, but we need an acceleration. So we want to find A of t. And how do we do that? Well, we have A of t, which is just the derivative of my v prime of t, which I don't have. So I actually need my velocity first. So I need my v of t, which is r prime of t. So I take the derivative. Okay, actually, before I do that, let me just write my r of t in vector form. So I'm going to say my r of t is, I think this was a cosine omega t, a sine omega t. So these are circular parametric equations. What else? Yeah, so now my r prime of t is the derivative of this thing. So a, or actually negative a, sine of this thing. So I actually forgot I had to use a chain rule here. So it's negative a w. Why I say w? A omega sine omega t. And then here the same idea. So we have a omega cosine of omega t. So that's my velocity. And now I can go straight into finding my acceleration, which is just the derivative of this thing. So let's quickly do it. Well, my negative a and w are constants, right? But here, this is not a constant. So this is cosine omega t. Looks like I do a chain rule again, so I square this. And then this one, again, I get my a omega. Now this is a negative because derivative of cosine is sine, negative sine. So we get negative a omega sine. And I think this is another chain rule that we have to follow. So we have w squared there. Okay. So we notice that, well, now we have it. Now we can find our force. So now let's find force. We'll call it F of t. I think F of t, yeah. So now my F of t is just my mass times my vector here, right? I'm gonna write the whole thing first. I think this was a sine, right? Yeah. Okay. And then what else can I do? Okay, so the textbook is a bit weird. It's telling me to take out my W. Okay, so it wants me to take out my negative and my W squared, but it wants me to leave out my A cosine of this thing. I don't know. Probably something to derive here. But this makes sense. Mathematically, this makes sense. Oh, so that's interesting. So now here we actually found a general formula. We say negative m omega squared r of t, right? Because this thing is just r of t in the beginning, right? This one. Oops, this one. So it's okay. It made a general formula. And what's next? So this shows that the force, so to contextualize this, or to make meaning out of this equation, the force acts in the direction opposite to the radius vector r of t, and therefore points towards the origin. And there's a, no, not calculus, there's a physics meaning of that. and it's called the centripetal force. Don't question me. I'm kidding. Yeah, I'm the one who's supposed to be asking questions because I haven't taken physics in a while. So yeah, the idea here is so the force. Okay, let me just write all of that. Acts in the direction opposite to, we're saying it's a radius vector here. We call it a radius vector because it actually starts from the origin, R of t, and let's just do hence. No one uses that anymore. Points to the origin. Okay, and so we call this a centripetal force. I might actually Google this a bit. You know, I'm gonna Google it. What in the world is centripetal force? So define it according to Google. It's the force that keeps an object moving in a circular path. So basically what we were trying to solve here. I'm gonna show the picture of what how this looks like visually with a geometric approach here. Okay. There, oh, why did it go there? So the picture is telling us that as we move, or as this particle moves along this circular path, well, the force is keeping it to the origin. So it's always going to point to the origin. And so in practicality, let me just, uh, let me, okay. So according to Google, or at least to my Google search, it's the force that keeps an object moving in a circular path. Because maybe if the force doesn't push it down, so like Earth, I can relate this to Earth, right? Because we have gravity and we're not going out of Earth or anywhere, then this is the center. So I think it's like pushing us down towards the center of Earth or something like that. But take that with a grain of salt, especially coming from me who doesn't know too much physics. Um, but yeah, so that's some, I guess, pretty interesting physics, cool physics application stuff on how we can apply this idea of, well, of velocity, speed, and acceleration. So yeah, I hope you guys enjoyed. Next, I'm gonna talk about, I'm gonna tease it a bit. Yeah. So the next thing I'm gonna talk about is a little bit more interesting in my opinion, because I made a video about it recently, and it's something about projectile motion. So I actually made a video here where I did something with projectile motion with Angry Birds. And this actually, wait, I'm gonna show it. So there's some cool stuff here. The idea is, so this is from you can just check one of my videos in calculus, and I did a part one and part two of this. But the idea is we want to use projectile motion equations in order to hit this Angry Bird to the pig. So wherever the pig is, we want the Angry Bird to hit it. And here we're assuming there aren't any, well, there aren't any obstacles and the like. So yeah, we did some pretty cool stuff here, and at the end we were able to find a formula. So this one, we're given some coordinates of the pig. So these are the coordinates of the pig: x pig, y pig, x pig. We need to launch our bird at a certain angle, and it has to be launched at some initial velocity. Okay, angle there. And we could switch the problem up. We could say, okay, we're given the coordinates of the pig and we're given the coordinates of the bird. Actually, not even the bird, because here we're assuming the bird's at the origin. Well, what's the velocity and the angle that we need in order to hit that pig? Or we're given the velocity and the angle. What point will it hit? Right? So that's just some cool stuff to find out. But yeah, so some interesting stuff here on projectile motions. I might resort to this maybe talk a little bit about it. I mean, I talked a lot right now, but yeah, pretty interesting stuff. Okay, so I'll see you guys in the next one. I'm gonna talk about projectile motion.